In the next few video clips, we're going to be concentrating on waves and some of the key concepts behind them. Our goal here is to understand one of Einstein's two key postulates that he enunciated in his theory of relativity, and that would be the principle of light constancy, the other one, of course, being the principle of relativity. So the principle of relativity and the principle of light constancy. To understand the principle of light constancy, we need to know a little bit more about light, and light, especially as it acts as a wave, and thus we need to go over a few of the concepts dealing with waves. So we'll say a few words about waves here in this video clip, and then a couple more after this one. I've listed some of the key terms we'll cover here, so you can write those down if you would like as we go along here. Many of them you've probably heard before, but you may not quite be sure exactly how, exactly what is a wavelength, what is frequency, and so on and so forth. These are terms we often use in everyday language, or semi-everyday language, I suppose. But if you really had to define it, you might say, I'm not quite sure exactly what that means. So we're not going to go into the whole long theory of waves, the different kinds of waves, and so on and so forth. We're just trying to hit the key concepts that we need to understand Einstein's approach here. So what I've drawn here is a typical periodic wave. A periodic wave is something that repeats its pattern. In fact, we could say, for our purposes, a wave is a disturbance in a medium that propagates along, or propagates through that medium, travels through that medium. Classic example, of course, would be water waves. And we could imagine, for this situation here, let's say we had a tank or something like that, or pond, whatever you want to imagine. And the dotted line here represents the normal still water level, the water level when nothing is happening. And then maybe we put our hand in there or have some sort of device where we can start moving it up and down, creating the ripples, creating the waves that will then travel, propagate outwards from our source of disturbance. So that would be our wave source, just our hand moving up and down, creating these waves going out, and we will draw the situation such as this. Obviously, we really need to do it in 3 dimensions, and it get a little more complicated, and the waves might die out as we go along. But we're imagining an idealized situation here, as we often do in physics. And so this would be the peaks and troughs of the water wave as it propagates along. So here would be the still water level. It goes up, and then you have a trough, and up and down, and up and down, and up and down, and so on and so forth. So again, a couple key concepts here. There is a medium involved. Okay, in this case, the medium would be water. It could be something like, you can imagine waves traveling as vibrations through a steel rod or steel bar, something like that. We talk about sound waves, of course, a disturbance or a pattern traveling through the air or a type of gas. And really 2 terms that we won't need, but you may have heard about: transverse and longitudinal. Transverse waves are where the disturbance is up and down, transverse. So if this is water here, the water molecules actually are moving up and down, up and down, up and down. And so that's a transverse type of wave where the wave motion is up and down vertically here. A longitudinal wave is where the medium, whatever the medium is composed of, in this case we'll do air, the motion is back and forth. For sound waves, actually, you have areas of higher density, where the air molecules group together more, and then areas of lower density. So this would be high density area, lower density, high density, lower density. But it's the movement of the medium, the air molecules in that case, are back and forth this way in the direction the wave is going. So it's longitudinal with the wave. And so there's certain concepts like that in terms of different types of waves, transverse, longitudinal, and so on and so forth. We won't actually need that, but you may think, water waves and sound waves, they are different. This is one of the ways they are different. Okay, so we're going to talk about essentially transverse waves, because light waves are transverse waves. So we'll learn about it a little bit later on, not in this video clip, but in a later video clip. But let's get some of these key concepts down. Again, a medium is involved. So in this case, we're going to imagine it's water. A periodic wave is something where the pattern or disturbance repeats itself. You have peak and trough, peak and trough, peak and trough. And again, we're just assuming that it doesn't die out or anything like that. It just continues on like that. So it's a periodic wave. Some other key concepts, the amplitude of the wave. The amplitude of the wave, as maybe you might guess, is just the up and down distance, measured usually from the center still point, as it were, if we're thinking about our water. So the amplitude in this case would be this distance there, or that distance there. Okay, so a wave with higher amplitude means you got higher up and down motion of the water molecules as the pattern, the disturbance goes along. The wavelength, the term we've all heard, but what exactly does it mean in this case? The wavelength is a distance, and it is essentially the distance, the easiest way to think of it is the distance between two peaks. So for example, from here to here is going to be the wavelength. Wavelength. And a symbol, we won't really have to use these symbols too much, but if you've had a little physics before, you may remember a common symbol for wavelength is the Greek letter lambda, lowercase lambda there. So that's the wavelength. Technically, the wavelength is the distance between any 2 points that are on the same part of the pattern. So we could also measure the wavelength from this point to that point, and if it's truly a periodic wave where everything is just repeating itself, exact same situation, then this distance here between those 2 points is the same as the distance between 2 peaks, is the same as the distance between, say, 2 troughs there, the negative peaks, and so on and so forth. So that's the concept of a wavelength. So when we talk about a short wavelength wave, it means it's compressed more. You have more oscillations up and down within a certain length, say 1 meter or 1 foot or whatever you want to measure with. Okay, so a short wavelength means you have more of these up and down oscillations in a given length, because that means the actual distance between 2 peaks is going to be smaller then, if you can get more of the up and down oscillations in a certain distance. A long wavelength wave is going to be something where, just the opposite. It's going to be a farther distance, longer distance between the 2 peaks or between the 2 points on the wave. So short wavelength, long wavelength. What about then the period? The period, now we're imagining here that, again, some of you who may have taken physics before know there's such things as standing waves. If you can get them going in your bathtub maybe, or on a string, waves on a string, where they just sort of look like they're stationary and not doing anything. And in this case, so we're going to assume our waves are traveling waves, so the disturbance is actually traveling along here. You can see the waves flowing through the water, as it were. And so the period then is as we're watching, let's just say this is our reference point right here. So here we are, standing right here, and we're watching the wave travel by us like that. And the period then, we have a little stopwatch, the period is going to be the time it takes from one peak until the next peak gets to us. Okay? So often measured in seconds, but any unit of time. So the period is going to be measured in seconds, or minutes, or hours, or years, or whatever you want, but often in seconds. Okay? So that gives you an idea, really, of how fast sometimes the wave is traveling, depending on a few other things as well. But that's the idea of the period. So period is measured in, we'll just say it's measured in seconds, really, or as I said, any unit of time. So wavelength measured, we'll say wavelength is measured in meters, centimeters, millimeters, nanometers if you want. Period measured in seconds. Now, another concept is the frequency. Okay? The frequency, in fact, often the period, I said we use the Greek letter lambda for wavelength. Often the period we use just a capital T for, since it's measured in seconds. The frequency is, if you think about it, you think, oh, what's frequency? How frequent is something? Okay? Well, what that really is saying here is how frequent are the up and down oscillations? That's what frequency means in the context of a wave. How frequent are those up and down oscillations? How fast are they occurring, in a sense, as this wave goes by me? So a high frequency wave is going to be one with a lot of oscillations in 1 second. Say I'm here and I'm counting the number of oscillations per second I see, the number of up and down movements that my wave is making as it goes by. If it's a lot of oscillations in a second, then I say that's a higher frequency wave. If it's fewer oscillations in a given time period, in a second or whatever it might be, that's a lower frequency wave. Okay? And in fact, frequency, I'll just put over here, frequency, we'll use the lowercase letter f for, although sometimes in your physics textbooks, again, if you've had physics before, another common letter is the Greek letter nu for that. We'll just use f, though, just to remind ourselves for frequency there. And it turns out, you might, if you think a minute here, there's a relationship between period and frequency. Okay? Let's think about that a minute. So we said the frequency is how many up and down motions we get, how many oscillations we get in 1 second. Okay? The period is how long it takes between peaks. So if I have a high frequency wave, right? So a high frequency wave, meaning I have a lot of up and down oscillations per second, it means the distance between peaks must be pretty short. The period must be small. Must be a small number if the frequency is high. And if the frequency is low, meaning I don't have as many oscillations per second, that means the period must be longer. There's a longer time between each peak, and so I'm not getting as many oscillations per second. And in fact, there's an exact inverse relationship between period and frequency. We can write period equals 1 over the frequency. So that if the frequency is a big number, if we talk about a high frequency wave, or really a high frequency anything, it means that the period is going to be very small. Got a big number down here, 1 over a big number makes this a very small number. On the other hand, if I say I have a low frequency something, like a low frequency sound, right, coming out of our bass speakers or whatever, this number is going to be much smaller. 1 divided by a small number gives me a bigger number over here in general. And so the period is going to be longer then. So high frequency, short period, low frequency, longer period. There's also a relationship between, for certain kinds of waves, like periodic waves we're talking about here, between the wavelength and the frequency and the velocity of the wave. We're not going to try to prove this or anything. We're just going to state it as a fact. And that is, if I've got a certain velocity, okay, so we'll call v the velocity of the wave here. It turns out that if you say, okay, here's a nice way to think about things. Think about the units of things. When you're trying to remember a relationship like this, it's going to be a very simple relationship, we'll see. But it's easy to sort of get it flipped around or the wrong way. And so think about the units involved. You say, okay, I'm told, or at least I know, that, I should say, I know, or at least I'm told, that there's a relationship between wavelength, frequency, and velocity. Okay, so velocity, I know, we'll say is in meters per second for our units, a length divided by a time. Frequency, note that if period is in seconds, frequency has to be inverse seconds. Okay, because they're inverse concepts, inverse relationship here. So frequency has units of 1 over seconds, or sometimes we say that, we write it like this in just sort of a little exponential notation, inverse seconds, but 1 over seconds, because it's the inverse of period. And wavelength, remember, is a length, as the name implies. So lambda is meters. Okay? So given those facts of what the units are for each of these, what the dimensions are, dimensions of distance over time, or inverse time, or distance for each of these, and we're told that there's a simple relationship between them, let's just think about this a minute and say, well, velocity is meters per second. Look what happens if I take the wavelength and multiply it by the frequency. I get meters per second. I have meters times 1 over seconds, and that gives me meters per second. In fact, that is a relationship here. We'll write it down here. A little more room. The velocity, this is for our periodic wave here, and technically even there's such a thing called harmonic wave. Again, for those of you who might have had a little physics before. If you haven't, don't worry. We're not going to have to use that concept. We just want to get the basic concepts of waves here. Velocity is going to be lambda, the wavelength, times the frequency. Because velocity is meters per second. Lambda is in units of meters. Frequency is in units of 1 over seconds. Instead of 5 there, S down there for seconds. Okay, just make that clear, that S being our abbreviation for seconds. And so this is just meters per second. And this is the relationship right here. So this is the key relationship. The velocity of the waves we'll be talking about is simply the wavelength times the frequency. And so know what happens here. If lambda gets big, let's say for a given velocity. So say we have a given velocity wave traveling along. If lambda is big, that means frequency has to be smaller, to make this work, and so on and so forth with that. You can go the other direction too. You have a high frequency wave. Big frequency means short wavelength. Okay, short wavelength, big frequency. So small wavelength, big frequency. Or big wavelength, lower frequency. Let's use the terms right. So low frequency, big wavelength, short wavelength, high frequency. Okay? And we'll mention those a little bit more maybe when we get to the light here. But those are the key concepts of our waves now. A few words about waves, just what wavelength is, the whole concept of a wave as a pattern, a disturbance propagating through a medium, and again, water is a classic example that we can use for that. And then just some of these simple relationships with waves between velocity, wavelength, frequency. And of course, we could put a period in here as well. Lambda times frequency is the same thing as, so we could say also, V equals lambda divided by the period is another way to write this, because instead of frequency here, period is 1 over the frequency. Frequency is also 1 over the period, the other way around. And so we can just mix and match those relationships, as long as, of course, we're doing it the correct way and have the units right there. Okay, so that's a few words about waves. We have a few more words to say about waves in the next video clip when we get into the concepts of phase and interference. So we'll do that next.